Preparing for a flight control engineer interview. You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you explain longitudinal stability and its impact on flight control design? Longitudinal stability is the aircraft's tendency to return to trimmed pitch and speed after a disturbance. I look at static margin, tail contribution, center of gravity range, and short period and phagoid modes. For control design, stable airframes need less augmentation, while relaxed stability vehicles need faster feedback and envelope protection. I would validate the model using aerodynamic derivatives, trim analysis, and frequency or time domain responses before tuning the controller. While answering, focus on static margin, center of gravity effects, short period and phagoid modes, trim conditions, aerodynamic derivatives, and how inherent stability changes controller bandwidth and augmentation needs. Question 2. Walk me through how you would design and tune a PID controller for aircraft pitch attitude. I start by defining the controlled variable, trim point, actuator limits, and required bandwidth. Then I build or identify a plant model and tune proportional gain for response, derivative for damping, and integral for steady-state error. I always add anti-windup, filtering on derivative terms, and rate limiting for actuators. After simulation, I verify step response, disturbance rejection, robustness margins, and performance across the flight envelope. Make sure to cover plant modeling, trim point selection, proportional, integral, and derivative roles, actuator limits, anti-windup, derivative filtering, stability margins, and testing across operating conditions. Question 3. How do you fuse IMU, GPS, magnetometer, and air data sensors for flight control? Sensor fusion turns noisy, biased measurements into reliable state estimates. I usually use high-rate IMU propagation for attitude and velocity, then correct drift using GPS, magnetometer, barometer, and air data updates. A Kalman filter or complementary filter handles different noise profiles and update rates. I pay close attention to frame transformations, timing, bias estimation, and outlier rejection. Good flight control depends more on trustworthy state estimation than on aggressive gains. In your answer, talk about complementary filtering, Kalman filtering, sensor update rates, bias estimation, coordinate frames, failure detection, latency, observability, and why raw sensor signals cannot directly drive control laws. Question 4. When would you use state-space control instead of classical transfer function methods? State-space control is best when the aircraft dynamics are coupled, multivariable, or need estimator-based feedback. Instead of controlling one loop at a time, I represent the system using states, inputs, and outputs, then check controllability and observability. Methods like LQR, pole placement, and Kalman filtering fit naturally. I still use Bode and root locus tools for intuition and robustness checks, but state space is stronger for modern integrated flight control systems. Be sure to mention multi-input, multi-output systems, state feedback, observability, controllability, LQR, pole placement, coupling between axes, and why classical methods are still useful for insight and margins. Question 5. What is gain scheduling, and how would you implement it in a flight control system? Gain scheduling handles the fact that one fixed controller rarely works well across the full flight envelope. I design controllers at representative trim points, often based on airspeed, altitude, Mach, flap setting, or angle of attack. Then I interpolate gains smoothly between points and test the boundaries heavily. The key is choosing scheduling variables that reflect actual dynamics. I also protect against discontinuities, sensor failures, and extrapolation outside validated regions. While answering, cover why aircraft dynamics vary with speed, altitude, Mach, weight, and configuration, how scheduling variables are selected, interpolation, validation, smooth transitions, and avoiding unstable gain jumps. Question 6. How do actuator saturation and rate limits affect flight control performance? Actuator limits can turn a stable linear design into a poor or even unsafe nonlinear system. Position saturation reduces available control authority, while rate limiting adds delay and phase lag. If an integrator keeps accumulating error during saturation, windup causes overshoot when authority returns. I handle this with anti-windup, command shaping, rate limiting, and control allocation logic. I also test aggressive maneuvers, gusts, and failure cases where actuators are most likely to saturate. Make sure to cover command limiting, rate saturation, phase lag, integrator windup, loss of authority, pilot-induced oscillations, control allocation, and simulation of worst-case maneuvers. Question 7. Describe a typical flight control architecture for a fixed-wing UAV. A fixed-wing UAV usually has nested loops. The inner loop controls roll, pitch, and yaw rates or attitudes at high frequency. Outer loops command altitude, airspeed, course, or path tracking at lower frequency. State estimation provides attitude, position, velocity, and airspeed. Guidance generates references, while control allocation maps commands to control surfaces and throttle. I keep failsafe, geofence, mode management, and health monitoring separate, but tightly supervised. In your answer, include inner attitude loops, outer guidance loops, navigation, state estimation, actuator mixing, mode management, failsafes, telemetry, and separation of real-time control from mission logic. Question 8. Explain how an extended Kalman filter is used in aircraft state estimation. An extended Kalman filter estimates aircraft states when the dynamics and measurements are nonlinear. In the prediction step, I propagate attitude, velocity, position, and sensor biases using the IMU and process model. In the update step, GPS, barometer, magnetometer, or air data measurements correct drift. The EKF uses Jacobians to approximate nonlinear behavior locally. Practical success depends on good noise covariance tuning, time synchronization, innovation gating, and robust handling of bad measurements. Be sure to discuss prediction and correction steps, nonlinear dynamics, Jacobians, covariance propagation, sensor noise modeling, bias estimation, innovation checks, and practical tuning challenges. Question 9. How would you evaluate whether an aircraft has acceptable handling qualities? Handling qualities measure how predictable, responsive, and workload-friendly the aircraft feels to the pilot. I evaluate modal damping, natural frequency, bandwidth, phase delay, control force gradients, and response to standard maneuvers. For piloted aircraft, Cooper-Harper ratings and MIL-STD criteria are useful references. For UAVs, I translate the idea into tracking accuracy and disturbance rejection. A technically stable system can still be unacceptable if it feels sluggish, oversensitive, or hard to manage. While answering, focus on pilot workload, damping, natural frequency, bandwidth, phase delay, MIL-STD handling criteria, control harmony, transient response, and flight test or simulation-based evaluation. Question 10. How do you assess stability margins and robustness in a flight control design? I never trust a controller just because the nominal simulation looks stable. I check gain and phase margins, crossover frequency, sensitivity functions, and closed-loop pole locations. Then I test robustness against mass properties, aerodynamic uncertainty, actuator dynamics, sensor delay, and atmospheric disturbances. Monte Carlo analysis is useful for finding weak corners. The goal is not maximum performance at one point, it is acceptable performance with enough margin across realistic uncertainty. Make sure to cover gain margin, phase margin, crossover frequency, Nichols or Bode analysis, model uncertainty, unmodeled dynamics, Monte Carlo testing, and why nominal stability is not enough. Question 11. How would you validate an aerodynamic model before using it for control law design? I validate the model in layers. First, I check geometry, mass properties, trim predictions, and aerodynamic derivative signs against theory, CFD, or wind tunnel data. Then I compare simulated responses with flight test or high-fidelity data from doublets, pulses, and frequency sweeps. I look at residuals, damping, natural frequencies, and control effectiveness. If mismatches remain, I update parameters through system identification and carry uncertainty bounds into the controller robustness analysis. In your answer, talk about wind tunnel data, CFD, system identification, flight test maneuvers, trim validation, aerodynamic derivatives, residual analysis, uncertainty bounds, and matching both steady and dynamic responses. Question 12. How do you design safe transitions between autopilot modes such as altitude hold, heading hold, and approach? Mode transitions are dangerous when references, integrators, or actuator commands jump unexpectedly. I design bumpless transfer by initializing controller states to match the current aircraft condition and ensuring command continuity. For example, entering altitude hold should capture current altitude unless a valid target is already armed. I define clear mode priorities, entry conditions, exit conditions, and failure behavior. Then I test transitions during turns, climbs, turbulence, sensor faults, and pilot override. Be sure to mention bumpless transfer, integrator initialization, reference capture, mode logic, command continuity, priority handling, pilot override, failure states, and clear verification of transition scenarios. Question 13. What strategies would you use to design fault-tolerant flight controls? Fault-tolerant control starts with identifying what failures must be survived. I use sensor redundancy, actuator redundancy, voting logic, reasonableness checks, and analytical redundancy where possible. Once a fault is detected and isolated, the system may reconfigure gains, redistribute control commands, or enter a degraded mode. The design depends on safety goals. Fail-safe may be enough for small UAVs, while transport or crewed systems often need fail operational behavior. While answering, cover redundancy, voting, analytical redundancy, fault detection and isolation, degraded modes, reconfiguration, actuator failures, sensor failures, fail operational versus fail-safe behavior, and certification considerations. Question 14. How would you structure SIL and HIL testing for a flight control system? I use SIL first to test algorithms quickly against plant models, requirements, and regression cases. Once logic stabilizes, HIL runs the flight software on target hardware with real-time simulation, sensor emulation, actuator interfaces, and communication buses. HIL reveals timing, quantization, I/O, and integration problems that pure simulation misses. I include fault injection, boundary cases, mode transitions, and long-duration runs. Every test should trace back to a requirement or hazard mitigation. Make sure to include software in the loop, hardware in the loop, real-time execution, sensor and actuator emulation, fault injection, timing checks, regression testing, coverage, and comparison with requirements. Question 15. What does DO-178C mean for flight control software development? DO-178C is not a coding standard. It is a software certification framework for airborne systems. It requires requirements-based development, traceability from system needs to code and tests, rigorous verification, configuration control, and documented reviews. The rigor depends on the software level, with Level A requiring the strongest evidence because failure could be catastrophic. For flight controls, I treat certification artifacts as engineering assets, not paperwork, because they expose ambiguity and reduce safety risk. In your answer, discuss software assurance levels, requirements traceability, verification independence, configuration management, reviews, testing rigor, tool qualification, model-based development considerations, and safety-critical process discipline. Question 16. How can aeroelastic effects or structural flexibility influence flight control design? Rigid body control models can miss flexible structural modes that appear at higher frequencies. If the controller bandwidth approaches those modes, it may excite wing bending, torsion, or even flutter-related dynamics. I account for this with aeroservoelastic models, sensor placement analysis, notch filters, and bandwidth limits. The controller must stabilize rigid body motion without injecting energy into flexible modes. This is a classic trade-off between responsiveness and structural safety. Be sure to cover flexible modes, flutter, control structure interaction, sensor placement, notch filters, bandwidth limits, phase margin, aeroservoelastic analysis, and why rigid body models may be insufficient. Question 17. How would you implement flight envelope protection in a control system? envelope protection prevents pilot or autopilot commands from pushing the aircraft beyond safe limits. I monitor variables like angle of attack, load factor, bank angle, pitch attitude, airspeed, and Mach. Protection can limit commands, reshape references, or override lower priority modes when boundaries are approached. The intervention should be smooth, predictable, and reversible. A good design respects pilot intent, but never allows commands that would cause stall, overspeed, or structural exceedance. While answering, focus on angle of attack limits, load factor, bank angle, airspeed, stall and overspeed prevention, command limiting, priority logic, pilot intent, and graceful intervention. Question 18. What should you consider when discretizing a continuous time flight controller for embedded implementation? Discretization is more than converting equations with a tool. I choose a sample rate high enough relative to control bandwidth and relevant dynamics, while leaving CPU margin. Then I account for zero-order hold effects, computational delay, sensor filtering, and actuator update rates. Tustin or zero-order hold discretization may be appropriate depending on the design. I also check quantization, overflow, numerical conditioning, and timing jitter, because embedded realities can erode stability margins. Make sure to discuss sample rate selection, zero-order hold, discretization method, aliasing, computational delay, quantization, numerical stability, sensor filtering, actuator update rates, and real-time scheduling. Question 19. How would you design a controller to reject wind gusts and turbulence? Gust rejection starts by understanding the disturbance spectrum and the aircraft response. I tune the controller with enough bandwidth to reject relevant disturbances, but not so much that it amplifies sensor noise or excites flexible modes. Air data or acceleration feedback can support gust alleviation, especially for load reduction. I test with Dryden or von Karman turbulence models and realistic gust profiles. The best controller balances tracking, structural loads, comfort, and actuator usage. In your answer, talk about disturbance models, bandwidth, feed forward from air data, gust alleviation, robust tuning, sensor filtering, structural loads, passenger comfort, and avoiding overreaction to noise. Question 20. During flight test, the aircraft shows unexpected oscillations after a control input. How would you investigate? I would first protect the test team by limiting the envelope or reverting to a safer mode. Then I would inspect flight data, command, response, actuator position, rates, sensor signals, and timing. Frequency analysis helps identify whether the oscillation is rigid body, actuator-driven, structural, or pilot-induced. I would compare results against simulation, check gains, signs, delays, filters, and saturation. Fixes should be tested incrementally, starting in simulation and HIL before returning to flight. Be sure to mention safety first, data review, frequency analysis, actuator and sensor checks, latency, gain errors, structural modes, pilot coupling, model mismatch, and incremental corrective testing. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.